Let's look at the graphs of exponential functions. So what you're seeing here in the graph, or graphs, I should say, there's two of them, on the right is that this one has the one that's increasing from left to right, and this one is decreasing from left to right. We would say that this is exponential growth, and then this one would be exponential decay, because one is going up and one is going down, okay? So when there is an up, our base is greater than 1. When the graph is going down from left to right, our base is less than 1. So when I look at this first example here, and I'm seeing that my base is the number that you're raising to the power, is 0.25, less than 1, this is a decay situation. So the graph is going to look like this one on the right, okay? Now, other notables here, and for any exponential function, when you plug in, I'm just going to zoom in here, when in that x spot, you plug in a 0, you're going to get just the number 1 for an answer, because any number to the power of 0 is a 1. Plug in a 1, you're going to get the b value, okay? So whatever that b value is will dictate whether you're going up or whether you're going down, okay? I see my b value is 0.25, so in this situation, the graph is going to look like, if I plug in a 0, I will get a 1. If I plug in a 1, I'm going to get 0.25. So this one looks like this. And from left to right, it goes down. Domain are the values we put in for x. For this one, the domain is negative infinity to positive infinity. We can put anything in. The range, well, we're going to go back to the graph for that, is what did we get out? Well, or even in the equation, you can see no matter what you put in for x, your answer to this is never going to be negative. So the range is going to be 0 to infinity, and I can't include 0 because there's no way for me to make this equation equal to 0, okay? And I have a horizontal asymptote because as x goes to infinity, my equation goes to, well, as x gets bigger and bigger and bigger, we're going to take that 1/4 or 0.25 and raise it to the power, and as that power gets bigger, that answer or that value gets closer to 0. So that means I have an asymptote at y equals 0. Domain, range, and asymptote. Okay? Now what happens if we shift? So we're going to go here. Just like other things or functions that we've done in the past, we have horizontal shifting, we can have vertical shifting. Okay? So here we're going to look at what is happening. Looks like the example is 2 to the x plus 1 minus 3. Well, before we start and dive into doing all the shifting and manipulations or transformations with this, what does y equals 2 to the x look like with no transformations attached? Well, when you plug in 0, you get a 1. When you plug in a 1, you get a 2. So it's going to look like this, right? Or this is 1, this is 2, and so on and so forth. Okay? Now, what's going on here? When we alter the x, it horizontally changes things. Okay? So I'm going to set this equal to 0 and solve it. This means that it is a left 1 unit shift horizontally. Okay? Then we have 2 to that. So think of this point and shifting it to the left. Think of this point, shifting it to the left. Okay? And then after that is done, we drop all of our values 3 units. Okay? So if that's the case, our graph is going to look like this now. Shifted to the left, so this point right here that's at a 1 goes left and then drops 3. So it goes left 1, drops 3, and lands here. This point, it's up at 2, it's going to go left 1, and then drops, so left 1, drops 3, and it's here. Negative 1, negative 2, negative 3, this graph, and now here. So my domain, again, I can put anything in the x spot, negative infinity to infinity. My range, looking at my graph, it looks like it can go as low as negative 3, but won't actually ever equal negative 3 because this stuff will never equal 0. Okay? up to infinity. And horizontal asymptote is what you're approaching. So it gets closer and closer to -3, but it never actually touches it. Okay, let's do it again for this next one. Oh, it's a solve. Okay, solve 42 equals 1.2 times 5 to the x plus 2.8 graphically. So we're gonna need a calculator for this. So I'm gonna grab my calculator. I'm gonna do, I kind of want to do does most, but there's a free calculator online that we can use. Let's grab it. Do I have it stored? There it is. Okay, I'm gonna use this one because chances are if you have a handheld calculator, it's this one. All right, so if we're gonna graph this, we're gonna go y equals, and remember one of the left side of the equation was just a 42. The right side of the equation is 1.2 times 5 to the power was just x. And then there was a plus 2.8 on the back end. Okay. Now I might have to alter the window. I don't think I'm going to for this one. Ooh, I might have to. Because on the left side of the equation, remember, was a 42. So let's bring this up to 50. There we go. Now we can see what you see in red is the second equation, or the right half of our equation, and then what's blue is the y equals 42 line, which is the left half of our equation. Okay. Now with your calculator, you can go second, intersect. Sorry, second, calculate, intersect. So number 5 in the list. It's asking us, if you look on the top corner here, it's asking us, hey, is 42 one of your equations? Hit enter. And it'll ask you for the other one. I touched my screen, so I mucked it up. And then it says you can guess if you want. I don't know. I don't care to guess. I just tell me the answer. So then hit enter again. And we can see that the intersection is when x is 2.16619. And it says the y value is 42, but we already knew that. So 2.16619. So we had one that went up and one that went over. X was 2.166 thousandths place, tens, hundredths, thousandths. Perfect. All right, moving on. This time, we're going to look at when there's a stretch in our graph. So if you'll notice here, we're going to take our function, which is b to the x, right, base to an exponent, and there'll be a numerical multiplier in the front end of it. So here they have labeled it a. In our first example here of this, there's a 4. So 4 is going to stretch all of those y values we would normally get. So every y value we would normally get, now we magnify by 4. So it has this vertical pull. So if you think about, let's just do y equals 1/2 x to the x. So normally we plug in a 0, we get 1. We plug in a 1, we get 1/2. So this is a decay that looks like this, right? Okay. Now, we would normally get a 1 when we plug in a 0. But when I throw a 4 in the front of it, when we plug in a 0, yes, this part becomes a 1, but now you're magnifying it by 4. So now it's here. When we plug in a 1, we would normally get 1/2, but now we're going to get 1/2 times 4, so that's a 2, okay? So it kind of has the same appearance, but it has been stretched vertically. Domain is still all real numbers. Range, we can see, is anything greater than 0. And asymptote is y equals 0. Okay. All right. Now, if the multiplier in the front is larger than 1, you have a vertical pull, so stretch. If it's less than 1, it's going to compress it. Okay. All right. Reflections. So notice right here, we're taking the traditional function, and all of those y values we would normally get, we're slapping a negative in front of. Okay. Now, there is a difference between putting a negative out front of the whole thing the traditional y value, right? And putting a negative in front of just the x component, okay? When you put a negative in front of the whole thing, like the first one here, we would take all of our original y values and they would now be the opposite. Well, if you have all of these y values, well, let's do this one, and you make them the opposite, they're now going to show up down here, down here, down here. Okay? For the second one that's listed here, when we put the negative just in front of the x, that means that the graph is going to behave and do what the opposite x would do. So what I mean by that is, if this is your normal one, this x is going to behave like this x, and vice versa. So it's a reflection over the y-axis, okay? So when it's out front, excuse me, it's going to go over the x-axis, and when it's just in front of the x, excuse me again, it's going to go over the y-axis. So there's the two differences. So let's look at number 5 here. Find the equation and graph the function g of x that reflects f of x over the x-axis, okay? So normal f of x, plug in a 0, you get a 1. Plug in a 1, you get 1/4. So there's the f of x function. G of x is going to take that f of x function and reflect it over the x-axis. So when you plug in a 0, you would get -1. When you plug in a 1, you would get -1/4. So it looks like that, reflected over the x-axis. Now, based on the two things that we highlighted in yellow above, when it reflects over the x-axis, we will see that by taking all of the original y values, and doing the opposite, okay? Domain, -infinity to infinity. Let's make that a little clearer. Range, well, if you look now at our graph of g, it looks like -infinity up to 0. And then the asymptote, y equals 0, like so. All right, so there's your equation, sketching of it, and domain, range, and asymptote. Okay, now, looks like we're going to throw it all in at one time. So if you look at this equation format, there's a lot going on, right? But we know what each piece of it does, so we can handle this, okay? All right. When we are given information or given an equation, I work like with the order of operations, starting with where the x is at, okay? All right, let's see what this number 6 example looks like. Write the equation for the function described below. Give the horizontal asymptote, domain, and range. All right, f of x equals e to the x is vertically stretched by a factor of 2, reflected across the y-axis, and shifted up. Okay. Well, this function, remember e is like 2.71, yada, yada, yada. Okay, so if you plug in a 0, you're going to get a 1. Plug in a 1, you're going to get that 2.718, blah, blah, blah. And it's a growth function like so. Now, what are we doing to it? We are stretching it vertically. So that means every y value we would get, we're making twice as large, okay? Reflected over the y-axis, which means all of these values are going to produce over here. So behave like the opposite x value. So now we have that. And then the whole thing is shifted up. So these are producing all the y values. And I want them to be 4 units more. Like that. Okay. All right. I have a problem from the book. All right, let's see. Find an exponential equation for this graph. Okay. Oh, if only they were easier. Let's see. Well, looks like it's going through 0, 5, and it says 1, 1. Okay. So I'm going to first just lay out our format. Maybe there's a multiplier. We have a base. We have an x. I don't see a well, it could be a horizontal shift. So I don't know yet. And then vertical shift, I'm going to say there's definitely one. Okay. I don't know if you've noticed, and I haven't overly pointed it out, but when we have a vertical shift, there's that plus D on the back end. It's always that plus number on the back end. So I can see that my asymptote is probably at 7. So I'm going to make this a 7. Okay. And now I see that base-wise, if I plug in, if I plug in a 0, I can find A. If I plug in a 0, I'm going to get a 5. So f of 0 is going to produce a 5. So 5 equals A. B to the 0 is a 1 plus 7. It looks like A then is -2 just by subtracting the 7, right? So now my equation is -2 times whatever the base is plus 7. I need to find the B to have my finished equation. So when I plug in a 1, we get a 1. All right. When I plug in a 1, we get out a 1. I can solve this for B. So I'm going to subtract 7, divide -2. Now I know my B. All right, what's my equation? Overall, f of x or y, whichever you want to write, the multiplier out the front was -2. The base was a 3. X, I'm doing it as if there's no horizontal shift. It doesn't appear to have one, but you never know. And then the whole thing was raised 7. So there's my equation. That one will work for that. Okay.